Welcome to the presentation of Detecting Patterns and Variability in Indian Winter Rainfall. I am Ayush Loda and I am with my friend Kamlesh Sawadekar will be presenting you regarding this topic. So let's move ahead. Here are our contents. Previously, we took course of Data Sciences in Earth Sciences under Professor Udit Bhatia. We learned how complex series and sequences can be written in form of matrices, how the transformation in matrix can reduce complexity. To have a hands-on experiment in course, we explored various time series and spatial series during assignments. Dealing with space and time series data separately is relatively simpler, but when it comes to data set which varies both in space and time, complexity increases significantly. Such dataset is called spatiotemporal dataset. One such example of spatiotemporal dataset is climate dataset. Climate dataset consists of spatial components of latitude and longitude and temporal components of time for the desired variable. The given example of precipitation dataset, owing to the huge volume of dataset that is being recorded, it is challenge for us to analyze this kind of data to find hidden meteorological pattern. One of the most important meteorological patterns which affect climatic conditions of India are El Nino and La Nina. To give you a feel of this fact, it is estimated that 60% of all the droughts in India in last 130 years have coincided with El Nino. During normal conditions, trade winds blow from east to west, push warm surface water towards Asia and piling it up in the Western Pacific Ocean. During the course of time, these winds weaken and the warm surface water moves eastward and reduces upwelling at the coast of South America. This phenomena is called El Nino. Since no clouds are formed in this event over Indian subcontinent, India receives poor rainfall during El Nino years. Eventually, these trade winds pick up again and sometimes they become even stronger than the normal ones. This led to flowing of warm water to the Western Pacific and upwelling of colder water towards Eastern Pacific. Such phenomena is called La Nina. Since clouds are formed over the Indian subcontinent due to the hot water in Indian Ocean, India receives rainfall during La Nina years. As El Nino and La Nina are opposite phenomena, their successive occurrences result into oscillation, and there is one neutral phase where there are no oscillations. Thus, El Nino, La Nina and neutral phase togetherly contribute and form El Nino Southern Oscillation that is also called as ENSO. Another phenomena is Indian Ocean Dipole. As the name suggests, dipole is when we have two extremes adjacent to each other. In this case, we have warmer side of ocean and colder side of ocean. Here, SST is sea surface temperature. Positive event, when warmer SST in Western Indian Ocean is relative to the Eastern Ocean, it is called as positive event. Negative event, when cooler SST in Western Indian Ocean relative to the East is the negative event. Positive IOD events are often associated with El Nino and negative IOD events are associated with La Nina. The main motto of our project was inspired from Mishra and paper. This paper is titled as A Prominent Pattern of Year-to-Year Variability in Indian Summer Monsoon Rainfall. The paper focuses on detecting patterns of ISMR using tools like EOF, MCA. We will discuss these methods more in further slides, but now we will first initially describe the results of this paper. The results of MCA between ISMR and global SST are as follows. The multivariate covariance analysis was performed between Indian summer monsoon and global sea surface temperature. The analysis results in more one shows that when this region heatens up, this region goes cool down, and since they are negatively correlated and it cools down, there is no formation of clouds over Indian subcontinent. In this case, we face El Nino. The plot B clearly describes that India is not receiving rainfall during El Nino years. The second mode is describing the La Nina event because there is hot region near Indian Ocean, which results into the cloud formation in India, and India receives rainfall during La Nina years. These are the EUF plots of Indian summer monsoon rainfall. Now, EUF and MCA modes show strong resemblance, and here researchers in the paper say that there is robust relationship between sea surface temperature SST and Indian summer monsoon rainfall, that is ISMR. Owing to Mishra and all paper, we tried to perform similar analysis on Indian winter rainfall and temperature dataset. We want to check our hypothesis of robust relationship between strength of winter and rainfall. Here we use temperature and precipitation data of Indian winters from November to February of time period 1952 to 2016. Now let's move towards methodology. First, we will look into EF analysis. This is an important analysis used in various problems of data science, which attempts to find the structure that explains maximum variance. Less number of vectors and structure conveys the same information without redundancy is the aim of EOF. We apply EOF on spatio-temporal dataset. Let's say that our data set is MXYT dataset, which varies in space and time. Now we will factorize this MXYT dataset using SVD. While doing SVD, singular value decomposition of this M dataset, which is our anomaly matrix or original time series, we get U as UFs. In sigma, there are diagonalizable eigenvalues, and these diagonalizable eigenvalues represent the amplitudes of UFs. And for the V, we get normalized PCs which show the amplitude of UFs. Now let's look into the example for understanding SVD and MCA in a better position. So let's see that we have a matrix 0, 1, 1, 1, 1, 0. Now we need to first form a square matrix out of it. There can be two ways to form square matrix out of it, that either we take A into A transpose or A transpose into A. So we get two matrices as the result of the two combinations. Now we will assume that A lambda is equal to I lambda, and we will get the respective eigenvalues and eigenvectors of A transpose. After calculating the respective eigenvalues and eigenvectors of A transpose, we say that the vectors obtained of the eigenvectors of A transpose are U1, U2, U3 respectively, and we get the lambdas. Similar analysis we can do for A transpose A, where we calculate the eigenvalues and the eigenvectors. These eigenvectors are termed as V1 and V2. Now we need to calculate the sigma. AV1 equal to sigma U1 is the formula through which we calculate our respective sigmas. For calculating the sigma, we can simply place A, V and U in this formula and we'll get the sigma. Hence, we have decomposed A into U diagonal of sigma 1 and sigma 2 matrix and V transpose matrix. And this is what is called SVD or singular value decomposition. Let's move ahead. From this plot, you can understand what does singular value decomposition really means. Methods to plot EUFs. One of the simplest way to plot EUFs is directly plotting the EUFs on the Indian or the world map. Another method can be EUF's amplitude is to take time series of principal component of an EUF. Normalize this time series to unit variance and then regress it against original dataset. Now, this map has shape of UF, but amplitude actually correspond to amplitude in real data with which this structure is associated. If we have any another variable for analysis, we can regress them across all the PC of one UF and show structure of several variables with correct amplitude relationship. For example, we can do the analysis for sea surface temperature and surface vector wind fields and can regress both can be regressed with the species of sea surface temperature. After completing various ways to plot EUFs, again we revisit EUF and see how EUF can be performed. EUF analysis, the method we discussed was the singular value decomposition. In singular value decomposition, EUFs, eigenvalues and PCs are directly obtained from the data matrix without the need of calculation to calculate the covariance matrix from the data first. Hence, calculation and understanding becomes very clearer, but it is preferred over smaller data sets. Another method is eigenvalue analysis method. Calculation gets tedious since procedure to calculate this matrix also involves calculating the covariance matrix and then they perform SVD over it. This calculation goes quite lengthy. If sample dataset is large, this method is preferred. If you have low computational power and sample dataset is large, you can use eigenvalue analysis method to calculate EUFs from the anomaly matrix.
So now we will discuss about maximal covariance analysis MCA. So let X and Y be the data matrices. Then first we begin finding the covariance matrix of X and Y, which is equals to XY transpose by N. Here N is the time dimension. Now similar to EUF, we apply SVD on covariance matrix, which will give us U into sigma into V transpose. This U and V are not similar to what we get as in UF. So what are these U and V? So U, column of U are the column spaces of covariance matrix and represent the structure in the covariance field of X, while V, the columns of V are the row space of CXY covariance matrix and are those structures in Y space that explain the covariance matrix. So this is how U and V are different than what it is in UF. And sigma is the diagonal matrix. The diagonal values are the singular values. The sum of the squares of the singular values is equal to the sum of the squared covariance between the original elements of X and Y. So what does this U and V actually tell us? What is their real significance really? The hypothesis is that these pairs of functions represent scientifically meaningful structures that explain the covariance between the two datasets. For example, the first UF in U and the first UF in V together explain most of the covariance or correlation between the variables X and Y. Now, how are principal components or PCs derived in case of MCA analysis? The principal components corresponding to the EUFs in U and V can be obtained by projecting the singular vectors EUFs onto the original data, like X star equals to U transpose into X and Y star equals to V transpose into Y. Further, the covariance between the kth pair of the principal component should be equal to their corresponding singular value. Now, beginning with the results, first we have the EUF results. We are presenting the first mode of EUF. Here we have n equals to 0 because Python starts counting from 0, and so this is the first mode. We see that the leading mode of EUF shows the precipitation patterns over North and South India oppositely correlated to the Central India, and these are the corresponding PCs. of the first mode of EOF. So this is the second mode of EOF, and we see that there is a strong presence of dipole, north-south dipole, over the Indian mainland. Next, moving to MCA results. MCA was performed between Indian winter rainfall and temperature. So first we will show the first mode of MCA analysis. So what is the singular vectors of precipitation, singular vectors of the temperature max and times expansion coefficients? So this singular vectors of precipitation, this means that this is the EOF of precipitation. This covers the part of the covariance matrix which is represented by precipitation, while this represents the part of covariance matrix which represents the temperature max. And these are the corresponding PCs. Remember U star, and we talked about X star and Y star. So this is the X star, the principal component of U, and this is the principal component of V. That means temperature max, principal component of temperature max, and principal component of precipitation. Similarly, we also plotted mode 2, say the second mode of MCA analysis. And now, going to the final interpretation, the final result, we found that the spatial pattern of MCA leading mode, the spatial pattern of MCA leading, spatial pattern of precipitation, spatial pattern of precipitation of leading mode resembles to EOF of Indian winter rainfall of mode 2. So this means if we follow the Mishra et al. Paper, this means that the results indicate the existence of robust pattern of variability in Indian winter rainfall that has consistent relationship with Indian winter temperature. So this finally means that the hypothesis we took was true, and we can say that there is possibility of a robust relationship between Indian winter rainfall and temperature. So future milestones. So what are we going to do further on this project? We have defined, for now we have defined the robust relationship between Indian winter rainfall and temperature above. So now we will go on defining the relationship, the positive correlation and the negative correlation with the help of plots of heterogeneous and homogeneous climatological patterns. Next, we will do MCA analysis on Indian winter monsoon and global temperature and obtain similar plots for understanding the ENSO phenomena which takes place in Pacific Ocean. Further, we would like to explore the mathematics of rotated EOFs, which deals with removing the orthogonality of EOF. Until now, we have used covariance EOF and plotted the results on the basis of same. But in future, if we restrict the dataset in boundaries of state or city, suppose we scaled it down more, we will not be able to reduce the complexity much. Hence, in this setting, we would like to go with correlation EOF. We would like to study about it and implement it similarly as we have done now. Next, we would like to regress the original species and obtain the SVD of rainfall with the original Olamalli and obtain the pure climatological maps. Similarly, we can regress the species on various parameters such as wind speed and obtain results which might be able to depict major climatological events in a more simpler way. So these were the future milestones. Thank you for viewing our presentation. So these are our individual contributions. Ayush Loda did the EOF analysis and plotting. Me, Kamlesh Sawadekar, did the MCA analysis and plotting. Both were done in Python. Both of us read various research papers and journals before reaching to these results. We would like to offer special thanks to Professor Udit Bhatia, who was our mentor and constantly guided us throughout our project course. Thank you.